Right, so in chapter 2 we were talking about sets, and near the end of the chapter we were talking about cardinality of sets, which is, finding out the number of elements in a set. And so we're going to segue now into chapter 6, which is about counting. So this is going to be sort of an introduction to a field called combinatorics, in particular what we call enumerative combinatorics. Combinatorics is a field of mathematics that deals with patterns and structures and collections of things, and one of the main topics in it is counting. So this will be an introduction to some of the basic ideas of counting. So we're going to be focusing basically on finding the cardinality of some finite set which is described. Back in 2.5 we were dealing with infinite things, countable, uncountable, so on. But we're turning our attention away from infinite to finite collections. So our first example here is to do with outfits. Suppose you have 6 shirts, 5 pairs of pants, 2 jackets, and 1 pair of shoes. If an outfit comprises one of each of these things, so 1 shirt, 1 pair of pants, 1 of the 2 jackets, and then your shoes, how many possible outfits can you create? So for this example, we have to use one of the basic rules of counting called the product rule. So the product rule says that the number of ways to do A and B in either order can be counted by multiplying the number of ways to do A times the number of ways to do B. So I like to think of this as like a sequence of tasks. If you have a procedure that involves do task A and do task B, and it doesn't matter what order you do them in, although even if it did, it wouldn't really change the result here. The way to count the number of different ways to perform the procedure is to multiply the number of ways to do task A times the number of ways to do task B. So in this example up here, what we're talking about doing is task 1, choose a shirt. Task 2, choose a pair of pants. Task 3, choose a jacket. And task 4, choose your shoes. How many ways are there to do those things? Well, we have 6 shirts, so there's 6 different ways that you can complete task 1, right? Choose a shirt, you've got 6 options. Choose a pair of pants, you've got 5 pairs of pants, so we're going to multiply by 5, because the number of different combinations of a shirt with pants is going to be 6 times 5. Okay, so the number of different ways to choose a shirt and a pair of pants is 6 times 5. Then we also have to choose a jacket, so we have 2 jackets, so we have to multiply this by 2. And finally, we have to choose a pair of shoes. We only have 1 pair of shoes, so we multiply it by 1. And so what we get here is the total number of different outfits, if that only consists of one of each of these things. And so the number of outfits in this case is 60. So we solved that problem. We counted that collection, not by counting 1, 2, 3, 4, 5, 6, 7, like we didn't count up to 60, right? So counting, I'm not talking about counting like that, right? I'm talking about counting as in enumerating, figuring out how many things are in a set. And we did it here by using this product rule. Okay, so let's look at the second example. Suppose that one representative must be chosen from either students or faculty. So you have a school or something, you've got some students and you've got some faculty in a group of people. If there are 63 students and 15 faculty, in how many ways can the representative be chosen? So we're only selecting one representative. The representative can come from either student, the student group, or from the faculty group. So in this situation, when instead of choosing a shirt and a pair of pants, right? Instead of and, it's more of an or situation. Choose either one student or one faculty. So for this, we're going to use what's called the sum rule. The number of ways to do A or B, but not both, okay? Which is essentially an XOR statement, A XOR B, right, is going to be the number of ways to do A plus the number of ways to do B. So what we've seen is essentially doing A and B corresponds to multiplying the number of ways together, whereas doing A or B, XOR in particular, without any overlap, is where you add them together, okay? This applies to the example above because we're assuming that the faculty and the student groups have no overlap between them. There's no person who counts as both a student and a faculty. If there were, then this solution would be different. But for our purposes here, we're just going to count the number of students as 63. So we have 63 different options for the representative from the student group, plus 15 options from the faculty group. We just add them together. Okay, so that you may have realized that was going to be the answer right away, but I'm using this as a simple example to demonstrate the sum rule. So I hope that kind of makes sense. So it's about 5 minutes. Let's do the second page. So we've learned the product rule and we've learned the sum rule. Those are the two most basic rules of counting. We're going to learn a few more rules, but first, in order for me to introduce the next couple of examples I want to go over, I need to introduce a new type of mathematical object. This is an object that may be very familiar to people who have done some programming, because it's used a lot in programming as well. And the type of object is a string. So a string is kind of like a set, except that in the case of a set, the order of the elements doesn't matter. But in the case of a string, the order totally matters. The order definitely matters. The other big difference is in a set, you don't bother ever stating repeated elements. Like you don't say X is in the set twice. You don't say XX. But in a string, you can repeat elements, usually, unless specified that you can't. But usually you're allowed to repeat things, and that's just fine. So a string is almost more like a sequence, if you're familiar with sequences from like Calc 2 or college algebra. So a string is an ordered sequence of characters or symbols, usually finite in length. Technically, you can talk about an infinite string, but for most purposes, we work with finite strings. So repeated characters are allowed unless specified otherwise, and those repeated characters could be what's the word? Consecutive, where you one after the other, or you could repeat a character multiple times throughout the string in different places. That's both fine. So the characters in question usually come from some specified set. So we talk about strings over a set, right, of characters, such as an alphabet or like a set of digits. So, like a letter string, the set of characters you're working with in a letter string is the set of letters. And you can use whatever alphabet you want, but I'm going to work with the set from A to Z. And I'm just going to use capital letters. If you wanted to make a distinction between lowercase and capital letters, you could. And then you'd have twice the number of possible characters. If you wanted to introduce like punctuation and stuff, you could do that. But for our purposes, I'm going to have letter strings refer to strings over this alphabet, which is just the capital letters from A to Z. And so examples of strings would be like A. You could have a string of length 1. That's fine. AA. That's a perfectly valid string, and it's different from the first one because it's length 2. You could have like it doesn't have to spell any word, right? It's just some random string of letters. So those are all perfectly valid strings. Let's put a couple of more A's at the end, just for good measure. Ab. So yeah, you don't need to pronounce it. That doesn't. But anyway, it's a string. Any string of letters would be a valid letter string. There's also this thing called lambda, the empty string. And within any set of strings over an alphabet, you can have an empty string, which is the unique string of length 0. So lambda is a Greek letter, but we use lambda there to represent a string of length 0, which has no characters in it. Okay, so just want to mention that. We're not going to do a whole lot with lambda right now in this chapter, but we will work with strings again in future chapters, and we will use lambda more later on. But I just wanted to tell you that it exists. So digit strings, for digit strings, you might have a set of characters, that represents all the possible digits we use for numbers, so 0 through 9. And then a digit string could be like 1099726. That's an example of a digit string of length. Here, I put a 0 on the end. 1, 2, 3, 4, 5, 6, 7, 8. So length 8. Okay, and a bit string in particular is a string that uses only the digits 0 and 1. So it's called a bit string because in computer science, a bit refers to a single piece of like digital information, which would be either a 0 or 1, which can, you can think of that as representing false or true, off or on. And so a bit string is sort of like a sequence of signals, each of which is either an on or an off, or a 0 or a 1. So, 0 is a valid bit string. 10 is a valid bit string. 01101 is a valid bit string, and so on, anything. So now that we've introduced strings, let's do a couple of examples. So these are going to be counting problems involving strings. We're going to say how many strings of a certain length satisfy some kind of conditions. So the first example is how many letter strings of length 4 start with A or start with BC. So we essentially have two cases. We have, case 1, start with A. Then we have case 2 over here, start with BC. So I'm going to map out the two cases in a kind of in a kind of a picture, if you will. Case 1 is like A, and then we have 3 blanks that we can fill with any letters we want. Remember, repeats are allowed unless we state otherwise. So nobody's saying we can't have another A in here. So the number of different options available for what you can put in that second position in the string is 26, because there's 26 letters in the English alphabet, which is the one that I'm using right now. So 26 letters available here. Okay. So that's case 1. We could have anything of that format. Case 2 is starts with BC. So we have BC. That's 2 letters. The length of the string is 4, so we only have two more letters that we can put on this string to complete it. So we have 2 blanks. So we have A, or we have A blank blank blank, or we have BC blank blank. Now, what I'm going to do is count the number of different possible strings in each case, and I'm going to use the multiplication rule. And I'm using the multiplication rule because I can think of this as a sequence of tasks. Decide what letter is going to go in the first blank, and then decide what letter is going to go in the second blank, and then decide what letter is going to go in the third blank. I have 26 options for the first one, I have 26 options for the second one, and I have 26 options for the third one. So it's 26 times 26 times 26, or I could write that as 26 cubed. So that's the number of options, a number of possible strings that satisfy case 1. For case 2, there's only 2 options, or there's only 2 blanks, so that's going to be 26 squared. Now, I have case 1 or I have case 2. So now I can use the sum rule, right? I can say, well, I've got 26 cubed options for the first one, plus 26 squared options for the second one. So I'm going to add those together with a plus here. And in order for me to use the sum rule, technically, I have to be in a situation where it's XOR, right? Where it's A or B, but not both. So I have to consider the possibility of overlap. Is it possible to have an example string which satisfies both of these cases? Well, in this situation, no, right? Because I can't have a string that starts with A and also starts with BC. So I'm going to write no overlap. No overlap between these two cases, right? No string will satisfy the conditions of case 1 and case 2 at the same time. So that means that my sum rule applies, and I can add these numbers together, and so my answer here is 18,252. And I'm not doing that in my head, of course. I have my notes over here. See? It's right there. I'm not a wizard. All right, so that's example 3. So now, for example 4, we're going to change it just slightly. We're going to change it to say, how many letter strings of length 4 start with A or end with BC? So again, we have 2 cases. Oops, case 1 and case 2. Oh, shoot. Hang on. Let me start over. Case 1 and case 2. In case 1, we're saying start with A. Okay, so that's going to be A blank 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 like it was before. But in case 2, we're saying end with BC. So it's going to be like blank blank BC. Like that. And why is it A and BC? I don't know. It's just I just picked some random things. But this problem is going to be different from the previous one because of the fact that there is now overlap. It's possible to satisfy the conditions of both cases at the same time by having a string that goes A and then some other letter, blank, and then BC, like that. So that both starts with A and ends with BC. So in this case now, the sum rule no longer applies because this is not an XOR situation. It's an OR, but it's now an inclusive OR because there is an overlap to consider. So for this, we now need what is called the subtraction rule. So this is a basic example of something called inclusion exclusion. And if you find this example sort of satisfying, if you find this idea kind of interesting and satisfying, then you can do a whole project about inclusion, exclusion, and its applications to other counting problems. So if you're into this stuff and you want to do it some more, consider that. One of the groups is going to end up studying that subject. So the example above has overlap between cases. What we need to do is count the number of things in the first case, number of ways to do case 1. That's going to be 26 cubed again. Count the number of ways to do case 2, which is 26 squared. Okay, and then we're going to add those together. But then what's happened is after adding these together, I have overcounted, which means that there's some cases, there's some particular strings that I have counted more than once, right? So like the string, for example, the string ADBC. That string has been counted twice so far in my summation that I've done here, because it counts as one of the 26 cubed strings in case A, and that string ADBC also counts as one of the 26 squared strings in case 2. Another example would be like ASBC, right? That string is also counted exactly twice. In fact, any string of the format A blank BC, where the blank is filled in with whatever letter you want, all of those strings, each and every one of those strings is counted exactly 2 times so far. So what I need to do is subtract off one copy of each of those strings in order to bring it back down from double counting those strings to single counting those strings, and then I will have the exact correct number of strings. So I'm adding together case 1 plus case 2 minus the overlap to account for this double counting that we have done and bring it back. That's why it's called inclusion exclusion, because you include and you include more than once, and then you exclude to like dial it back down and bring it back to sort of the correct value. As you like extend the idea of inclusion exclusion, it ends up being like you include and then you subtract and then you add again and then you subtract and then you keep kind of fluctuating back and forth until you zero in on the correct value. And so there is an extended version of this that you can study in the project if you want to. So what do we need to subtract here? Well, now that in the overlap situation, now that there's only one blank, I just need to subtract 26 strings, because there's 26 options for what could go in that blank. So my total value here is going to be 26 cubed plus 26 squared minus just 26, and that's 18,226. Of course, you will be able to use a calculator on a test. So, all right. So I'm going to finish up this video with one more thing. It's getting kind of long. I'm going to finish up this video with drawing an example of inclusion exclusion in terms of sets. So if you have 2 sets like this, okay, let's call this set A and set B. If you want to do, like take the union and then count the number of elements in the union, what you're going to do is you're going to count the number of elements in set A. All right, there we go. There's the number of elements in set A. And then you're going to count the number of elements in set B. I'm going to do that. There we go. There's the number of elements in set B. We've counted all of set A. We've counted all of set B. Here's set A here. Here's set B here. So we're adding together the cardinalities of those 2 sets. But then, as you can see, there's potential overlap between the 2 sets, and that overlap has been counted twice. So the problem is I need to get back in there, and I need to like subtract off some of this. I need to go back in there and be like, hey, remember this part that we counted? Forget that. Let's just subtract that off. I'm not going to subtract both of them. I'm just subtracting one copy of what is in there. I'm just going to remove that. So I'm removing the number of elements in the intersection so that I go from having counted it twice to having counted it exactly once. And then that brings me back to the correct value of the correct number of elements in the total union. So there's a nice visualization for how you do this, like subtraction rule or inclusion exclusion. All right, so that's the main lesson on counting, basic counting rules. So what I want you to do now is try these exercises. Okay, I have 4 exercises that apply some of these rules. Give it a shot. In the next video, I'm going to go over these.